In September 2023, a telescope detected a molecule that had no right to exist there. Not on that planet, not in those concentrations. Not unless something alive was producing it right now, on a world 120 light-years away, around a star that is not our sun. The molecule was dimethyl sulfide. On Earth, only living organisms make it in measurable amounts. Marine phytoplankton release it as a metabolic byproduct across every ocean on this planet. It is the reason the sea smells the way it does when wind comes off open water. No volcano generates it, no lightning storm builds it up. No known geological process produces dimethyl sulfide in concentrations that instruments can detect from space. And JWST found it, tentatively, carefully, demanding more confirmation, in the atmosphere of a world that should not have it if chemistry alone were running the show. The team that made the detection did not celebrate. They checked the data again, then a third time. Then they asked independent teams with no stake in the result to check it too. Because if the signal held, if it survived scrutiny and years of additional observation, the implication sitting quietly at the end of that data chain was so large it barely fits inside a single sentence. We might not be alone. Not confirmed, not proven. Science does not move that fast or that carelessly. But for the first time in the history of the species, a real instrument had pointed at a real planet and returned a signal that life would explain more naturally than anything else in the known chemistry of the universe. This is what JWST was built toward, even if no one said it in exactly those words at the budget hearings and congressional briefings. The telescope was built to see what came before, to find the first galaxies, to read the earliest light that the universe ever emitted. But it saw something else along the way, something that might change everything about what we think we are in relation to everything else that exists. To understand what JWST found in 2023 and why it matters in ways that extend far beyond a single molecule on a single planet, you have to understand what the telescope is, how it reads alien skies, and why no instrument built before it could have made these discoveries, even in principle. The story begins not in space, but in a conference room in Baltimore in 1996. A small group of astronomers gathered and asked a question that sounded almost impossibly ambitious for the technology of their time. What would it take to observe the very first galaxies that ever formed? Hubble had been operating for 6 years and was already transforming every branch of observational astronomy. But Hubble had limits written into its physics that no engineering improvement could overcome. The earliest light in the universe, the glow from the first stars and the first galaxies, has been traveling for over 13 billion years before reaching any telescope we can build. That journey stretches it. The expansion of space itself pulls the wavelengths apart, shifting visible and ultraviolet light into infrared, into heat, into frequencies the human eye cannot detect, and that Hubble's detectors were never calibrated to capture. To see the first billion years of cosmic history required a fundamentally new telescope, tuned to infrared wavelengths, operating from a location cold enough that its own thermal emission would not blind its detectors. The telescope that emerged from that 1996 conversation took 25 years to build. It cost $10 billion across its development program. It came within a single congressional vote of being canceled during a budget crisis in 2011 when cost overruns had stretched the program far beyond its original projections. On Christmas Day, 2021, it launched from the Guiana Space Center in Kourou, French Guiana, riding an Ariane 5 rocket, and began a 29-day journey to a gravitational equilibrium 1.5 million kilometers from Earth called the second Lagrange point, L2. At L2, the combined gravitational influence of the Earth and the Sun holds a spacecraft in stable orbit, moving in precise lockstep with Earth around the Sun, always maintaining the same orientation relative to both. JWST unfolded itself there over those 29 days in a sequence of 344 single-point failures, each a deployment that had to succeed exactly or the mission was lost. Mirror segment by segment, sunshield layer by layer, instrument by instrument, until it became the largest, coldest, and most precisely engineered observatory that humanity had ever placed in space. Its primary mirror spans 6.5 meters assembled from 18 hexagonal segments, each coated in gold because gold reflects infrared light more efficiently than any other material, and each adjustable to nanometer precision by actuators that move slower than the hour hand of a clock. Its sunshield stretches to the size of a tennis court across 5 layers of Kapton film thinner than a single human hair, separating the sun-facing side of the telescope, which reaches 85 degrees Celsius in constant irradiation, from the cold side where the instruments operate at minus 233 degrees Celsius. At that temperature, just 40 degrees above absolute zero, the telescope's own infrared glow drops below the threshold that would contaminate its measurements of the cosmos. It becomes cold enough to detect heat from planets orbiting stars 100 light-years away. It becomes sensitive enough, according to one frequently cited comparison, to detect the heat of a bumblebee on the surface of the moon. The instrument that transformed atmospheric science is not the mirror itself. It is a device inside the telescope called NIR SPEC, the near-infrared spectrograph. NIR SPEC does not take pictures. It does something more precise and more scientifically powerful than any camera. It splits light into its component wavelengths, the way a glass prism splits white sunlight into a rainbow, but with a spectral resolution so fine that the individual absorption features of specific molecules appear as distinct dips in the resulting spectrum. Every molecule in the universe absorbs and emits light at specific wavelengths determined by quantum mechanics and the physics of chemical bonds. Carbon dioxide absorbs infrared at 4.3 microns, always, everywhere in the universe. Water vapor has its own absorption pattern, a fingerprint spread across the near-infrared spectrum that no other molecule exactly replicates. Methane absorbs at 3.3 microns with a distinctive shape that planetary scientists can identify with the same confidence a forensic analyst identifies a fingerprint lifted from a crime scene. Sulfur dioxide, dimethyl sulfide, carbon monoxide, sodium, potassium. Each molecule has a unique spectral signature as fixed and identifying as any fingerprint, determined by the fundamental quantum properties of its atomic bonds. When a planet passes in front of its star during an event called a transit, a thin shell of atmosphere at the edge of the planetary disk filters the starlight passing through it. That filtered light travels across interstellar space, enters JWST's mirror, reflects down into NIR SPEC, and gets spread across a detector array. The wavelengths absorbed by atmospheric gases appear as dark lines against the bright background of the stellar spectrum. Read those lines and you have read the atmosphere. You have in effect sniffed the air of another world without leaving Earth. This technique, transmission spectroscopy, had been theorized for decades before any instrument existed that could do it with sufficient precision. Hubble attempted it on the largest, most accessible targets. The signals were always there, barely, at the edge of detectability, suggestive but never conclusive enough to build firm scientific claims on. JWST performs transmission spectroscopy with a clarity that makes the best Hubble atmospheric results look like reading a book through 3 meters of muddy water. The upgrade is not incremental, it is categorical. The first target JWST pointed its full atmospheric power toward was not a habitable world and was never intended to be one. WASP-39b was chosen because it was the ideal calibration target. A hot gas giant, known since 2011, thoroughly studied by Hubble and Spitzer for over a decade, orbiting its star in just 4.055 days. At that orbital distance, tidal forces lock it with one hemisphere always facing the star. That hemisphere heats to over 900 degrees Celsius. Nothing biological survives those conditions. But WASP-39b is large and inflated, its atmosphere puffed out by intense stellar radiation to a radius that makes transmission spectroscopy dramatically easier than on any smaller, denser, more Earth-like world. It was the ideal first target, a planet where results could be compared against prior Hubble observations to validate JWST's performance, where errors could be caught before they contaminated measurements of worlds that actually mattered for the search for life. What JWST found on WASP-39b was not what anyone expected from a calibration exercise. In August 2022, the team announced the first unambiguous detection of carbon dioxide in any exoplanet atmosphere in history. CO2 had been hinted at by Hubble years earlier. The hints were always murky. The JWST spectrum showed it with such clarity that the absorption feature stood above the noise floor like a mountain against a flat horizon. That single result would have justified a Nature paper and a NASA press conference. But NIR SPEC kept reading the spectrum. Water vapor appeared, consistent with earlier suggestions, but now measured precisely rather than inferred from ambiguous signals. Sodium appeared. Potassium appeared. Carbon monoxide appeared. The atmosphere of WASP-39b was assembling itself in the data, molecule by molecule, like a chemical inventory being taken from 700 light-years away. Then came a molecule that nobody had expected to find cleanly on this target. Sulfur dioxide, SO2, sitting at 4 microns in the transmission spectrum, a small but fully unambiguous dip that could not be reproduced by any atmospheric model that excluded photochemical reactions. Why does the detection of sulfur dioxide on a hot gas giant 700 light-years away matter for anything beyond the chemistry of that specific planet? Because SO2 cannot form in darkness. Sulfur dioxide on WSP-39b is not a primordial remnant locked in the atmosphere since the planet formed. It is being produced continuously, right now, driven by ultraviolet photons from the host star-striking hydrogen sulfide and other sulfur-bearing molecules in the upper atmosphere, breaking their bonds and forcing the freed atoms to recombine into new configurations. That process has a name: photochemistry. On Earth, photochemistry governs the formation of the stratospheric ozone layer that protects the surface from ultraviolet damage. It governs the smog that forms over cities when sunlight hits vehicle exhaust and triggers chains of reactions that produce ground-level ozone. It governs the breakdown of methane before it can accumulate to concentrations that would dramatically accelerate the greenhouse effect. It governs the color of sunsets, the formation of certain cloud types, the chemistry of the upper atmosphere that no balloon has ever sampled directly. Scientists had assumed for decades that photochemistry must operate on exoplanet atmospheres exactly as it operates on Earth's, driven by the same quantum mechanical rules that apply everywhere in the universe. No instrument had confirmed it until JWST read WSP-39b's spectrum. In December 2022, the complete dataset was published across 5 simultaneous papers in Nature, each addressed by a different section of the massive international collaboration assembled for the WSP-39b Early Release Science Program. The paper focused on sulfur dioxide, led by Dr. Shangmin Tsai at the University of Oxford, walked through the photochemical network in detail. The models predicting SO2 production from UV photodissociation of hydrogen sulfide matched the observed concentrations with a precision that left no room for alternative explanations. Photochemistry worked the same way on WSP-39b as it works here, and that result established something deeper than the presence of one molecule on one hot gas giant. It established that the laws governing atmospheric chemistry on Earth are not local peculiarities of our specific environment, they are universal. Physics does not change depending on which star you orbit. Chemistry runs on the same quantum rules around a G-type yellow dwarf 700 light-years away that it runs on around our Sun. The universe applies its laws consistently, without exception, across every atmosphere that has ever formed around any world. WSP-39b was proof of concept. K218b was the discovery that changed the entire conversation about what JWST might eventually find. The planet had been detected in 2015 by the Kepler Space Telescope, confirmed in 2017, and assigned to the category planetary scientists call sub-Neptune or mini-Neptune. Its mass had been measured at 8.6 times Earth's mass, its radius at 2.6 times Earth's. Those numbers place it in a category that has no analog anywhere in our solar system. Too large to be a rocky super-Earth with a thin atmosphere like Mars or Venus. Too small to have undergone the runaway gas accretion that created Neptune or Uranus. Sub-Neptunes are extraordinarily common throughout the Milky Way. Survey data from Kepler suggests they are more common than any other category of planet, more numerous than Earth-sized rocky worlds, more numerous than gas giants, more numerous than anything that fits our solar system's familiar classification scheme. The most abundant type of planet in the galaxy is one we cannot study in our own backyard, because we simply do not have one. K2-18b orbits a red dwarf star designated K2-18, completing one orbit every 33 days at a distance that planetary models place within the habitable zone. In 2021, Dr. Niku Madhusudan at Cambridge's Institute of Astronomy published a paper in the Astrophysical Journal proposing a new class of potentially habitable world that he called the Hycean planet. The name combines hydrogen and ocean. The hypothesis was specific and testable. Some sub-Neptunes, beneath their thick hydrogen-dominated outer atmospheres, harbor global liquid water oceans, warmed from above by stellar radiation filtered through the hydrogen envelope, and from below by geothermal heat released by radioactive decay in the planet's rocky core. These internal oceans might be warm enough, chemically rich enough, and geologically stable enough over billions of years to support the emergence and persistence of life. K2-18b fit the predicted profile of a Hycean world almost exactly. When JWST turned its instruments toward K2-18b across multiple observing campaigns in 2023, the question being asked was whether the Hycean hypothesis had any basis in observable atmospheric chemistry. The answer came back in September 2023, published in the Astrophysical Journal Letters, and it required NASA to schedule a press conference. The spectrum of K2-18b showed carbon dioxide, Clear, confirmed, not tentative. It showed methane. Also clear, also confirmed, present in concentrations consistent with the predictions made for Hycean world chemistry. Carbon dioxide and methane coexisting in a hydrogen-rich atmosphere creates a specific chemical fingerprint. On a world with no ocean, with a dry rocky surface, with chemistry driven purely by geological outgassing, the ratio of these molecules would be different from what the models predict for an ocean-bearing planet. The ratio observed on K2-18b was consistent with what Dr. Madhusudan's team had predicted for a world with a liquid water ocean beneath its hydrogen atmosphere. This was not proof of an ocean. It was consistency with the hypothesis. In science, consistency with a testable prediction is the first step toward building the kind of evidence that eventually becomes a conclusion. Then the team reported a third molecule, dimethyl sulfide, DMS, detected at approximately 2 sigma statistical significance. 2 sigma is not a discovery in physics or astronomy. It represents roughly a 1 in 20 probability that the signal is a statistical fluctuation in the noise rather than a real molecular absorption feature. 5 sigma is the conventional threshold of confirmed discovery in these fields, representing a 1 in 3 million probability of a false positive. The team knew this. They reported the DMS signal anyway, with complete and explicit acknowledgement of its tentative status, because the specific identity of the molecule they were reporting made silence the wrong choice. Dimethyl sulfide, CH3SCH3, on Earth produced almost exclusively by living organisms, specifically by marine phytoplankton releasing it as a metabolic byproduct when they process dimethyl sulfoniopropanate, a compound that helps regulate osmotic pressure in their cells. DMS is what gives the ocean its characteristic smell. No confirmed abiotic mechanism generates dimethyl sulfide in measurable concentrations in Earth's atmosphere. Not volcanoes, not lightning. Not photochemistry operating on sulfur compounds, not any geological process studied across 150 years of atmospheric chemistry research. If DMS is genuinely present in K2-18b's atmosphere, and if it forms there through the same mechanism it forms here, something is continuously producing it. Something that runs on biochemistry, something biological. The scientific community responded to the K2-18b announcement with the measured, careful, appropriately skeptical reaction that the evidence warranted. Dr. Sarah Seeger at MIT, one of the world's foremost experts on exoplanet atmospheres and biosignature science, noted publicly that 2 sigma signals require confirmation before any interpretive weight can be placed on them. The history of science is littered with signals that seemed real at low statistical significance and vanished as more data accumulated. The N-rays of 1903, claimed by French physicist René Blondelot based on observations that were never replicated by independent researchers, turned out to be products of observer bias and expectation, not real phenomena. The arsenic-based life announcement of 2010, briefly presented as evidence that life could substitute arsenic for phosphorus in its biochemistry, collapsed completely under attempts to replicate the original experiments. The phosphine signal in Venus's atmosphere, announced in September 2020 as a potential biosignature and reported in a paper in Nature Astronomy, shrank dramatically in subsequent reanalyses of the same JCMT data and remains deeply contested years after the original announcement. Science learns from each embarrassment by demanding more confirmation, more independent verification, more robustness against alternative explanations before accepting any extraordinary claim. The DMS detection on K2-18b was being held to exactly this standard, Dr. Jonathan Fortney at UC Santa Cruz raised a concern more specific to K2-18b's unusual atmospheric context. The planet's hydrogen-rich atmosphere creates strongly reducing chemical conditions, fundamentally different from Earth's oxidizing, nitrogen-oxygen-dominated environment. Reactions that cannot occur in our atmosphere might generate DMS through purely abiotic pathways in a hydrogen-dominated environment, particularly if sulfur compounds are being photochemically processed in unusual ways by the red dwarf star's different spectral output. A molecule that means biology in one chemical context might mean geology in another. Dr. Madhusudan's team acknowledged this possibility explicitly in the published paper, noting that the abiotic chemistry of hydrogen-rich planetary atmospheres remained incompletely modeled, and that further theoretical work was needed to determine whether DMS could accumulate to observed concentrations through non-biological processes on a world like this. They were not claiming detection of life. They were reporting a signal that demanded explanation, and noting that the most familiar explanation, the one that works on Earth, is biological. The question left open was whether K2-18b's very different chemistry offered explanations that did not require invoking biology. Beyond the DMS debate, the broader K2-18b result was already reshaping how atmospheric scientists thought about the diversity of potentially habitable environments in the galaxy. Before the Heysen hypothesis and the K2-18b observations, the prevailing assumption in habitability research was that a world needed to closely resemble Earth to support life. Rocky surface, thin atmosphere of nitrogen and oxygen, liquid water in oceans of moderate depth, a yellow dwarf star at the right distance. The specific combination of factors that Earth possesses had come to seem like the template, the configuration that life required. K2-18b violated every element of that template. No rocky surface, a hydrogen atmosphere that would be toxic to any aerobic organism we know of on Earth. An ocean so deep, if it exists, that the pressure at the bottom would be extreme by any terrestrial standard. A red dwarf host star emitting a very different spectrum than our Sun, and yet the atmospheric chemistry was consistent with habitability. If the DMS signal confirmed the chemistry was consistent with biology, the implication was not subtle. Life, if it exists on K2-18b, evolved under conditions so different from Earth's that the biological processes running there would be fundamentally alien to anything we know. Different biochemistry, different energy sources, different molecular machinery, but running on the same fundamental chemistry of carbon, hydrogen, oxygen, nitrogen, sulfur, the same elements that build every organism on Earth, because those are the elements the universe makes in abundance and distributes throughout every planetary system. The template was not Earth specifically. The template was chemistry plus time plus energy. And those three ingredients are extraordinarily common across the universe. While the K2-18b debate continued in journals and at conferences through 2023 and into 2024, JWST was simultaneously conducting a parallel investigation with very different immediate goals, but equally profound long-term implications. In February 2017, an international team announced the discovery of 7 Earth-sized planets orbiting a single ultra-cool red dwarf star located 40 light-years from Earth. The star was named TRAPPIST-1 after the ground-based telescope in Chile, the Transiting Planets and Planetesimals Small Telescope, that first identified it as a candidate for planetary transit observations. The 7 planets were labeled B through H in order of increasing orbital distance. 3 of them, planets D, E, and F, orbit within the habitable zone where liquid water can exist on a planetary surface given the right atmospheric conditions. The announcement was treated immediately as one of the most significant exoplanet discoveries ever made, 7 Earth-sized worlds around one star. 3 in the habitable zone, at distances that place them among the most accessible potentially habitable planets known. At 40 light-years, close enough for detailed atmospheric study with the telescope, then under construction in French Guiana. TRAPPIST-1 became the highest priority atmospheric characterization target in exoplanet science almost immediately, and retained that status through JWST's launch, deployment, and first years of operation. But a fundamental question shadowed every optimistic projection about the system's habitability prospects from the moment of discovery. TRAPPIST-1 is a red dwarf, an M-type star barely large enough to sustain nuclear fusion, the most common class of star in the Milky Way, and also, critically for planetary science, one of the most magnetically violent. Red dwarfs flare, not occasionally, frequently, unpredictably, and with energies that can briefly match the total luminosity of the star in the most extreme events. A large stellar flare releases energy primarily in ultraviolet and X-ray wavelengths, hard radiation that strips atmospheric gases from planets orbiting within range by heating the upper atmosphere to the point where gas escapes the planet's gravitational hold and bleeds into space. Earth is protected from the solar wind that carries similar particles from our Sun by a powerful magnetic field generated by its molten iron core. The TRAPPIST-1 planets are tidally locked to their star, meaning they rotate once per orbit, keeping one face always toward the star and one always away. Tidal locking slows the planetary rotation dramatically compared to Earth, and planetary magnetic field strength depends partly on rotation rate. Slower rotation can mean weaker magnetic shielding. Weaker shielding means more atmospheric erosion over geological time. Whether any planet in the TRAPPIST-1 system retained its atmosphere across billions of years of red dwarf activity depended on a combination of magnetic shielding, atmospheric replenishment from volcanic outgassing, and the specific history of the star's activity level. JWST's first task at TRAPPIST-1 was to answer the most fundamental question before asking any other. Do any of these planets still have atmospheres? The answer for TRAPPIST-1b arrived in May 2023. It was not encouraging, though it was not entirely unexpected. Dr. Thomas Green at NASA's Ames Research Center led the team that analyzed secondary eclipse observations of the innermost planet. A secondary eclipse occurs when a planet passes behind its star as seen from Earth, temporarily blocking its own thermal emission from reaching our telescopes. By comparing the combined infrared light of star plus planet before the eclipse to the light of the star alone during it, astronomers can calculate how much infrared radiation the planet itself is emitting from its heated surface. That emission constrains the temperature of the planet's day side, and the temperature distribution across the planet reveals whether an atmosphere exists to transport heat from the star-facing hemisphere to the permanently dark night side. On a bare rock with no atmosphere, the substellar point, the spot directly below the star, heats to its maximum possible temperature, and the temperature falls sharply away from it. Heat does not travel laterally across a vacuum. On a planet with atmosphere, winds carry thermal energy around the planet, lowering the peak dayside temperature as heat moves toward the night side. TRAPPIST-1b's dayside temperature was measured at approximately 500 Kelvin. That number matched the model prediction for a bare rock absorbing stellar radiation and re-emitting it as heat with nothing present to redistribute that energy elsewhere. Had a substantial atmosphere existed, the measured temperature would have been lower. It was not lower. TRAPPIST-1b appears to have no atmosphere of any significance. The stellar wind and flare activity of its red dwarf host had, over billions of years, stripped away whatever gases the planet once held, leaving exposed rock heated directly by a star it can never turn away from. The result was sobering but scientifically important for what it implied about the outer planets. TRAPPIST-1b is the innermost planet, receiving more stellar radiation and more stellar wind than any other world in the system. If any planet were expected to lose its atmosphere first, TRAPPIST-1b was the obvious candidate by simple physics. The question that mattered was whether the loss had propagated outward to the habitable zone planets farther from the star. TRAPPIST-1c provided the next piece of the atmospheric puzzle in 2024. The second planet, orbiting every 2.42 days at roughly twice the distance of TRAPPIST-1b from the star, receiving approximately half the stellar radiation that the innermost planet receives. Still too hot for liquid water by most models, still almost certainly tidally locked, but the secondary eclipse data told a meaningfully different story than TRAPPIST-1b. Dr. Sebastian Ziba at the Max Planck Institute for Astronomy in Heidelberg led the analysis. The measured dayside temperature of TRAPPIST-1c was lower than the prediction for a bare rock. Not dramatically lower, but enough to rule out the bare rock scenario at the same statistical confidence that TRAPPIST-1b's data confirmed it. Something was either reflecting more stellar radiation than bare rock does, redistributing heat away from the substellar point, or both. A thin atmosphere could explain the reduced temperature. A highly reflective surface, perhaps covered in mineral dust or salts left behind as any water present slowly evaporated, could also contribute. The result did not confirm an atmosphere on TRAPPIST-1c, but it ruled out the thick Venus-like carbon dioxide atmosphere that some theoretical models had predicted for inner planets of red dwarf systems. And it left open the possibility of an intermediate atmospheric state, denser than bare rock implies but far thinner than anything Venus maintains. Perhaps a remnant atmosphere, thinned by stellar activity across billions of years, but not yet completely stripped. Perhaps a dynamically maintained atmosphere, replenished by volcanic outgassing at a rate roughly matching the loss to stellar wind. Each inner planet result tightened the constraints on what the habitable zone planets farther out might look like. If the erosion that stripped TRAPPIST-1b was severe enough to leave bare rock, and if TRAPPIST-1c retained even a partial atmosphere despite similar exposure over the same time span, then perhaps the outer planets, shielded by greater orbital distance and receiving less stellar bombardment, had fared better still. The data was building a gradient, from bare to progressively more retained, moving outward through the system toward the worlds that mattered most. TRAPPIST-1d, E, and F remained at the top of every habitability priority list through all of this inner planet work. TRAPPIST-1e in particular drew the most scientific attention. It orbits every 6.1 days at a distance that places it squarely in the center of the habitable zone around its star. Its estimated mass is 0.62 Earth masses. Its estimated radius is 0.92 Earth radii. Slightly smaller and less massive than Earth, but similar enough in bulk properties that its interior structure might closely resemble ours. If it has a molten iron core generating convective flows, it might produce a magnetic field. If it has a magnetic field, the stellar wind that stripped TRAPPIST-1b might have been partially deflected over the planet's history. If atmospheric erosion was slowed by magnetic shielding, and if volcanic outgassing replenished atmospheric gases lost to space, and if the habitable zone distance provided enough warmth without too much radiation, TRAPPIST-1e might have maintained liquid water on its surface for billions of years. Each of those conditional statements is genuine and unresolved, but none of them is assumed impossible. Each is a testable prediction that JWST observations are actively constraining, transit by transit, spectrum by spectrum, as the science team accumulates enough signal to distinguish between competing atmospheric models. A detection of water vapor on TRAPPIST-1e, when it comes if it comes, will be announced differently than any previous atmospheric result. Not as a photochemistry confirmation or a Hyson world consistency check. As evidence that one of the nearest potentially habitable worlds we know carries liquid water in some form in its present-day atmosphere. That result alone would reshape the entire research agenda of planetary science for the decade following it. Beyond TRAPPIST-1, a second rocky world candidate was accumulating atmospheric data that pointed in a surprisingly optimistic direction. LHS-114-OB orbits a quiet red dwarf 48 light-years from Earth every 24.7 days. Its mass is 6.98 Earth masses. Its radius is 1.73 Earth radii. A super-Earth, denser than a mini Neptune, likely rocky throughout, positioned within the habitable zone of a star whose flare activity is lower than that of most red dwarfs its size. In 2024, JWST observations of LHS-114-OB produced a result that the team described with unusual scientific optimism, given the general caution that characterizes published claims in this field. The thermal emission data was most consistent with a planet that had a nitrogen-rich atmosphere, similar in dominant composition to Earth's, rather than a bare rock or a thick carbon dioxide-dominated environment. Nitrogen does not absorb or emit light in ways that JWST can directly detect. But the presence of a nitrogen-dominated atmosphere changes the thermal profile of the planet in ways that the emission data constrained. The best fit models required some atmosphere to match the observations. The simplest atmosphere consistent with the data was nitrogen-dominated with a modest fraction of other gases. Dr. Charles Cadieux at the Université de Montréal, who led the LHS-114-OB analysis, was careful in how he presented the result. The data preferred atmospheric models over bare rock models. The preferred atmospheric composition was nitrogen-dominated. The uncertainty was still substantial, and alternative interpretations could not be completely ruled out. But the direction of the evidence was pointing toward habitability rather than away from it, which for a rocky world in a habitable zone at 48 light-years was a result that warranted continued intensive observation. LHS-114-OB joined K2-18b and the TRAPPIST-1 habitable zone planets on the short list of worlds where JWST was actively closing in on answers that would matter beyond the technical literature. On a parallel track entirely removed from habitability research, JWST was demonstrating capabilities that none of its designers had fully anticipated when the instrument specifications were first written in the late 1990s. Super-Earths, planets ranging from roughly 2 to 10 Earth masses, make up the most common category of planet in the galaxy by most estimates. They are also the least understood, precisely because our solar system contains none of them. Earth at 1 Earth mass is the largest rocky planet we have in our backyard. Neptune at 17 Earth masses is the smallest ice giant. The vast middle ground between those two extremes is populated throughout the galaxy, with worlds we have no local examples of to study directly. In May 2024, JWST published results for 55 Cancri EA that immediately became one of the most discussed atmospheric detections in the program's history. 55 Cancri E orbits a sun-like star just 41 light-years away, detected in 2004 and studied continuously since then with every available instrument. Its mass is 8.8 times Earth. Its orbital period is 17.7 hours. 17.7 hours. It orbits so close to its star that its surface temperature exceeds 2,000 Kelvin, well above the melting point of basalt, of granite, of any rock we know. The dayside surface is a magma ocean, a global lake of molten rock with no solid ground anywhere across the hemisphere that faces its star. Previous observations had hinted at the possibility of a thin atmosphere, but without the precision to confirm it against alternative explanations. JWST's thermal emission maps settled the question and then immediately raised a larger one. The data showed that the hottest region of the planet's dayside was not centered at the substellar point as it would be on a bare rock. It was shifted westward, displaced in the direction of planetary rotation, consistent with a dynamic atmosphere redistributing heat in a specific pattern, not a static temperature map. A weather system. On a world covered in molten rock at 2000 Kelvin, an atmosphere was moving. The composition remained uncertain and is still being modeled. Possibly carbon monoxide and carbon dioxide outgassed continuously from the magma ocean beneath as rock boiled away into the atmosphere. Possibly more exotic compounds produced by the photochemistry of a very different starting chemistry than any atmosphere planetary scientists had modeled before. But the redistribution was real, the atmosphere was dynamic, 55 Cancri E has weather, a world of molten rock has clouds, has winds, has atmospheric circulation patterns. And none of the models published before JWST observed it had predicted this clearly enough to make it an expected result. The cumulative effect of WSP-39b, K2-18b, TRAPPIST-1b and 1c, LHS-1140b, and 55 Cancri E across 3 years of JWST observations was to fundamentally revise the theoretical framework that planetary scientists use to think about what atmospheres exist and what they do. Before JWST, the models predicted that atmospheres on small planets orbiting red dwarfs would mostly be gone, stripped by stellar activity. Some would persist if magnetic shielding was strong enough. The ones that persisted would be relatively simple chemically, dominated by whatever molecules outgassed most readily from the rocky interior. Photochemistry would be present but weak, given the low UV output of red dwarfs. The detection of complex chemistry on WSP-39b demonstrated that photochemistry was stronger and more consequential than models had assumed, even on worlds orbiting stars with higher UV output. The K2-18b results demonstrated that hydrogen-rich Hycean world atmospheres could support complex carbon chemistry and potentially even biological chemistry. The TRAPPIST-1 interplanet results demonstrated that bare rock and thin remnant atmospheres existed side by side in the same system, separated by orbital distance, which meant the outer habitable zone planets might be in very different states. The 55 Cancri E results demonstrated that even worlds with surfaces no model predicts could support life were more atmospherically complex than anyone expected. The pattern is not that every planet has an atmosphere. The pattern is that atmospheres are more persistent, more chemically active, and more diverse than the models built before direct observation were assuming. When theory meets data, and data consistently outperforms theory in complexity and richness, the lesson is not that the data is wrong. The lesson is that the universe is more generous in what it allows than the models that human minds constructed to describe it. The philosophical weight of what JWST is doing rarely surfaces in the careful technical language of published atmospheric science papers. Scientists are trained to understate, to hedge, to qualify, to present observations without allowing interpretation to run ahead of evidence. But in conference talks, in informal interviews, in the acknowledgement sections of papers where the conventions relax slightly, the weight shows through. Dr. Madhusudan, in a 2023 interview given after the K2-18b paper was published, described what it felt like to process the atmospheric data and see the DMS signal appear in the spectrum. He said the team ran the analysis multiple times before allowing themselves to discuss out loud what the signal might mean. Not because they doubted the measurement, because they understood what it would mean if the measurement held. A molecule that life makes, in the atmosphere of a world that might have an ocean, 120 light-years away, around a star that will burn for another 40 billion years. The signal was tentative, 2 sigma, requiring confirmation. But it was the first time in human history that a real instrument had pointed at a real planet and returned data that required the word biological to be included in the scientific conversation about what was observed, not as a confirmed answer, as a hypothesis that the data did not permit science to rule out. That is an entirely new position for humanity to occupy. For all of recorded history, the question of whether life exists beyond Earth has been a philosophical question, answerable only with statistics and inference, and the frustrating logic of probability calculations that produce no direct evidence. JWST has made it an observational question. One that can be answered, in principle, by collecting enough photons from the right sources and reading the molecular record they carry. That shift from philosophical to empirical is not incremental, it is categorical. It is the difference between wondering and knowing. And we are standing at the boundary between those two states right now, closer to the knowing side than any generation before us has ever been. There is a deeper question beneath the biosignature search that rarely appears in press releases and that scientists discuss mostly with each other in quieter settings. What would confirmation of life on another world actually mean? Not the sociological question of how institutions and governments and religious traditions would respond to the announcement. The scientific question of what it would tell us about the structure of the cosmos. If life exists on K2-18b in a hydrogen ocean beneath an alien atmosphere around a red dwarf star, under conditions bearing no resemblance to the environment where life began on Earth, the implication extends far beyond the specific discovery. It means life is not fragile. It means that the chemistry of life, the carbon-based molecular machinery that converts energy into structure and self-replication, works under a wider range of conditions than any current biological theory assumes. It means that the specific details of Earth's history, the late heavy bombardment, the collision that formed the moon, the timing of the Great Oxygenation Event, the evolution of the eukaryotic cell, all of those events that seemed necessary preconditions for complex life were implementation choices, not requirements. One evolutionary pathway among many that all lead toward the same destination. Biology, wherever chemistry and energy and time exist together in sufficient abundance and stability. And chemistry, energy, and time exist together on a scale the human mind cannot fully hold. 200 billion stars in the Milky Way alone, most of them orbited by planets. Most of those planets orbited for billions of years. Most of those planetary systems containing the same carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus that life here uses. If life is robust enough to emerge in K2-18b's alien ocean, then the number of living worlds in this galaxy is measured not in thousands or millions, but in numbers so large the words for them lose their meaning. The universe would be saturated with life. Not necessarily complex life, not necessarily technological life, but life in the fundamental sense of self-sustaining chemical systems that extract energy from their environment and use it to maintain and replicate their own molecular structure. That possibility changes everything about how we understand our position in the 13.8 billion year story of the cosmos. We would not be an accident or an anomaly. We would be an instance. One expression of a process the universe executes wherever it can, as reliably as gravity assembles hydrogen into stars, and nuclear fusion assembles hydrogen into heavier elements. Life, on that view, is not something that happened to the universe. It is something the universe does. The biosignature framework that JWST is using to search for life is worth understanding in its own right, because it determines what the telescope is actually looking for and why certain detections would matter more than others. A biosignature is not a living organism detected directly. No telescope we can build has the resolution to see microbes on another planet, or forests, or any biological structure smaller than a continental scale feature. A biosignature is a chemical state that biology would explain more readily than any known abiotic process. Earth's atmosphere is the most accessible and best studied example. Our atmosphere contains molecular oxygen, O2, at 21% concentration. It also contains methane, CH4, at trace but measurable concentrations of about 1.8 parts per million. In chemistry, oxygen and methane react with each other. Oxygen oxidizes methane, converting it to carbon dioxide and water vapor. Left to run without replenishment, this reaction would consume all the atmospheric methane in roughly 10 years. And the oxygen would then begin oxidizing other reduced species, eventually reaching equilibrium. Oxygen and methane do not coexist in equilibrium. Their simultaneous presence in Earth's atmosphere is maintained entirely by biological activity. Photosynthetic organisms, from cyanobacteria to every green plant that has ever grown, produce oxygen from carbon dioxide and water as a byproduct of their energy metabolism. Methanogenic archaea and bacteria, in ocean sediments, wetlands, rice paddies, and the digestive systems of animals, produce methane from organic matter through anaerobic metabolism. Both gases are produced continuously by different branches of the biosphere, and both are continuously removed by chemical reactions. The balance point where they coexist depends on the production rates, which are set by biological activity. Without life, the balance point shifts. Methane disappears, oxygen eventually finds other things to oxidize, and its concentration drops as well. Oxygen plus methane in a rocky planet atmosphere at the right distance from a stable star is the single most robust atmospheric biosignature that planetary science has identified. No confirmed abiotic process produces and maintains both gases simultaneously in an oxidizing planetary atmosphere over geological time. JWST cannot yet measure this combination on a rocky habitable zone planet. The rocky planets being studied are too small, their atmospheric signals too faint at the distances involved for current integration times to resolve the full molecular inventory at the precision needed. But JWST is approaching that capability for the best targets. And the generation of instruments being built now on Earth and in space are designed specifically to make that measurement. The extremely large telescope being constructed on Cerro Armazones in Chile by the European Southern Observatory will have a 39-meter primary mirror when it achieves first light in the late 2020s. 39 meters of light-gathering power, operating behind the thin, dry atmosphere of the Atacama Desert at an altitude where most atmospheric turbulence is below the observatory. Its METIS instrument, the mid-infrared ELT imager and spectrograph, is designed partly to perform transmission spectroscopy on rocky planets orbiting nearby stars with a sensitivity that extends JWST's reach to smaller, fainter atmospheric signals. The Giant Magellan Telescope at Las Campanas Observatory in Chile is targeting first light in the late 2020s with a 24.5-meter mirror, assembled from 7 8.4-meter primary mirror segments. Its GMTNIRS spectrograph covers near-infrared wavelengths relevant to the molecular inventory of planetary atmospheres. The 30-meter telescope, delayed by legal and cultural disputes over construction on Mauna Kea in Hawaii, but still planned and funded, would add further capacity to the ground-based atmospheric characterization effort. In space, the Habitable Worlds Observatory was identified as the highest priority new mission in NASA's 2020 Astronomy and Astrophysics Decadal Survey. Its design is still being refined, but the scientific mission is explicit. Build an observatory capable of directly imaging rocky planets orbiting sun-like stars within about 25 light-years of Earth and using coronagraph technology to block the direct starlight, reveal the reflected light from those planets, and take spectra of their atmospheres directly, without waiting for transits. The Habitable Worlds Observatory is designed to search for oxygen and water vapor together in the reflected spectra of Earth-like planets, the combination that would indicate a living biosphere in the most unambiguous terms currently known to planetary science. The timeline for this observatory extends into the late 2030s or 2040s, depending on development funding. But the program is not aspirational in the way that interstellar missions are. The physics is understood. The technology is achievable within existing engineering capabilities. The targets are identified and within range. The only remaining question is whether the funding and political will to build it can be sustained across the decade of development it requires. Somewhere between the current JWST results and the future Habitable Worlds Observatory observations, the answer to the oldest question in science is going to emerge from data rather than philosophy. The question has been asked in every language that has ever had words for stars and for living things. Are there other worlds with life on them? The question sounds simple. The answer requires measuring atmospheric chemistry from interstellar distances with precision that requires the coldest, most complex scientific instruments ever constructed, pointed at stars for months at a time, accumulating photons one at a time until the signal of a molecule emerges from the noise. It requires knowing what molecules mean life and which merely mimic it. It requires distinguishing biological from geological, from photochemical sources of the same compound, on worlds where we cannot collect a sample, cannot land a probe, cannot verify in any way except through the light that reaches us across light years of empty space. The process is slow by any human timescale. Each transit observation of a rocky habitable zone planet accumulates signal for a few hours, and then the geometry changes and the observation ends. Building enough signal to measure an atmosphere at the required precision takes dozens of transits, sometimes hundreds, spread across years. JWST's observing schedule is one of the most contested resources in science. More than 7 times as many scientifically excellent proposals are submitted each year as can be accommodated in the available hours. Every hour spent on TRAPPIST-1E is an hour not spent on LHS 114, OB or K 2-18b, or the next world on the priority list. The choices made in those scheduling decisions reflect human judgment about which questions are most important to answer before time runs out on the instrument's operational lifetime. Most of the scientists who study these worlds believe the biosignature search deserves that time, because the answer, when it comes, will not belong to any field or any institution or any country or any generation. It will belong to the species. In a November night in 2022, during the processing of WSP-39b data from the first full observing season, a researcher working late pulled up the composite transmission spectrum and scrolled through the wavelength coverage from 0.5 to 5 microns. The sulfur dioxide feature sat at 4 microns, a clear dip against the noise floor, produced by photochemistry operating in an alien sky around a star that our sun will never visit. She had worked with Hubble atmospheric data for years before JWST launched. She described the experience in an interview months afterward. Not triumph, vertigo. The feeling of realizing that the photons arriving at the detector, after traveling for 700 years across interstellar space, were carrying information about a chemical process that runs the same way in that alien atmosphere as it runs in Earth's stratosphere. Same quantum mechanics, same molecular bonds? Same photodissociation and recombination reactions, just driven by a different star orbiting a different part of the same galaxy. The universe runs on universal laws. That seems obvious when stated as an abstract principle. It becomes viscerally real when a spectrum shows you a molecule produced by ultraviolet light on a planet that cannot be reached in any human lifetime, and the molecule's fingerprint is identical to the one produced by the same process 15 kilometers above your head. We are not a special case in the universe's chemistry. We are an instance, one expression of a chemistry that works wherever the conditions allow it. And the conditions, JWST is showing us, allow it in more places and more configurations than any previous generation of scientists had reason to expect. The dimethyl sulfide signal in K2-18b's spectrum is not a confirmed answer. It is a door left open by data. A door that JWST, given enough time and enough photons, has the capability to push further open than any instrument in history. Through that door, if the signal confirms, is a world with an ocean and something living in it 120 light years away. Through that door, if it fades with more data, is a better constrained picture of what K2-18b's atmosphere actually contains, and what Heysian world chemistry looks like in the absence of biology. Both outcomes advance the search. Neither is a failure of science. Science does not fail when a hypothesis is tested and found incomplete. Science fails only when observation is ignored in favor of preferred conclusions. JWST is observation, stripped of everything else. Photons from alien atmospheres spread into spectra, read by instruments cold enough to detect heat from across interstellar distances. The universe leaving its chemical record for the first instrument we have ever built sensitive enough to read it. We are 13.8 billion years into the universe's story. We are 4.5 billion years into Earth's chapter of that story. We are a few decades into the era when we can read the atmospheric chemistry of other worlds. The molecule appeared in a spectrum. The question it carries with it has been waiting for an answer since the first human looked up at a night sky and felt the full weight of what they were looking at. Something else out there, asking the same question from the other direction? We do not know yet, but we are closer to knowing than we have ever been. And getting closer, one spectrum at a time, one transit at a time, one photon at a time, across the patient, in different, astonishingly chemically generous universe that built us and everything we have ever used to look back at it. The search for biosignatures is not only a technical challenge, it is a philosophical one disguised as a measurement problem. Before we can find life on another world, we have to agree on what we would accept as evidence that life is there. That question sounds simpler than it is. On Earth, we know life when we see it because we evolved alongside it. We recognize the movement of animals, the growth of plants, the smell of microbial activity in soil after rain. We have 3.8 billion years of shared evolutionary history with every organism on this planet, and that history gives us intuitions about what living things look and smell and behave like. None of those intuitions transfer across interstellar distances. From 120 light years away, no telescope can see an organism. No instrument can detect movement or behavior or metabolism directly. What we can detect is chemistry. Specifically, chemistry that is out of equilibrium, in ways that require an ongoing input of energy to maintain. Life is, at its most fundamental level, a process that maintains chemical disequilibrium against the universe's relentless tendency toward equilibrium. A living cell converts high-energy molecules into lower-energy molecules, extracting usable energy from the difference, and uses that energy to maintain its own structure, replicate its molecular machinery, and resist the thermodynamic pressure toward disorder. The waste products of that process, the exhaust of metabolism, accumulate in the surrounding environment, and change its chemistry in ways that can be measured. On Earth, the most consequential example is oxygen. Photosynthesis converts carbon dioxide and water into glucose and oxygen. The glucose powers cellular metabolism. The oxygen is released as waste. 2 billion years of photosynthetic activity by cyanobacteria transformed Earth's atmosphere from a reducing environment dominated by methane and nitrogen into the oxygen-rich environment that made complex animal life possible. The oxygen in Earth's atmosphere is, in the deepest sense, the excretion of photosynthetic organisms accumulated over geological time. It is the chemical fingerprint of a biosphere. From 120 light-years away, with the right instrument, that fingerprint is detectable. This is why the simultaneous presence of oxygen and methane in a rocky planet atmosphere is considered the most robust biosignature known. Not because life is the only conceivable source of either molecule, but because life is the only known process that can maintain both molecules simultaneously in an oxidizing atmosphere at concentrations above detection threshold. The probability of finding that specific combination by geological coincidence without a biosphere continuously producing and replenishing both gases is small enough that planetary scientists treat it as functionally zero. JWST cannot yet make this measurement on rocky worlds. The signal-to-noise ratio is not there yet for the small, faint planets in habitable zones at distances relevant to the current target list. But every improvement in observing strategy, every additional transit observation, every refinement in data reduction technique brings the measurement one step closer to possible. There is a number that planetary scientists who work on biosignature detection think about constantly, though it rarely appears explicitly in published papers. It is called the false positive rate. A false positive in biosignature science is a detection that looks biological but is actually produced by abiotic chemistry, by geology, by photochemistry, by instrumental artifacts, by anything other than life. Venus has sulfur dioxide in its atmosphere, produced by volcanic activity, not biology. Mars has methane detected intermittently, possibly from geological reactions between water and iron-containing rocks, not necessarily from life. Europa, the ice moon of Jupiter, might have hydrogen peroxide and oxygen in its thin surface atmosphere, produced by radiation chemistry, not biology. Each of these examples demonstrates that individual molecules, even molecules associated with life on Earth, can be produced abiotically under the right conditions. This is why biosignature science has moved increasingly toward atmospheric combinations rather than single molecules as the primary detection target. Oxygen alone is not enough. Venus-like planets can have oxygen produced by photodissociation of water vapor and subsequent hydrogen escape without any biology. Methane alone is not enough. Geological sources produce methane on Mars and potentially on ocean worlds throughout the solar system. Dimethyl sulfide alone is not enough, which is why the K2-18b signal has generated debate about whether hydrogen-rich atmospheres might have abiotic DMS production pathways not present in Earth's oxidizing environment. The combination matters, the context matters, the host star matters, the orbital distance matters, the planet size and composition matter. The presence of liquid water matters as a constraint on temperature and chemistry. Building a compelling biosignature case requires assembling multiple lines of evidence that collectively point toward biology more convincingly than toward any known abiotic alternative. That assembly is what JWST is beginning, planet by planet, molecule by molecule, building the observational database that future instruments will use to make the definitive measurements. The red dwarf problem is the shadow that falls across every discussion of habitable exoplanets within JWST's reach. Nearly every promising atmospheric target identified so far orbits a red dwarf. TRAPPIST-1 is a red dwarf. K2-18 is a red dwarf. LHS-1140 is a red dwarf. Ross-128, Teegarden Star, Proxima Centauri, all red dwarfs. They dominate the target list for a simple geometric reason. Red dwarfs are far more numerous than Sun-like stars, making up approximately 70% of all stars in the Milky Way. Red dwarfs are also smaller, making their planets produce larger transit signals relative to the star's disk. And red dwarfs are cooler, meaning their habitable zones sit much closer to the star, and planets in those zones transit more frequently, allowing more observations to be accumulated in a given amount of telescope time. The physics conspires to make red dwarf planets the easiest targets for transmission spectroscopy by a large margin. But the stellar environment around a red dwarf is fundamentally different from the environment around a sun-like star. Red dwarfs are magnetically active, particularly when young, producing far more ultraviolet and X-ray radiation relative to their total luminosity than our sun does. They flare frequently and unpredictably, sometimes brightening by factors of tens or hundreds in the UV within seconds. Each flare sends a pulse of hard radiation and energetic particles outward through the planetary system. For a planet orbiting close enough to be in the habitable zone of a cool red dwarf, these flares arrive with intensities that would be devastating for any unshielded surface life. Earth's ozone layer shields the surface from our sun's UV output. A similar ozone layer around a TRAPPIST-1 planet would be constantly stressed and periodically stripped by the more energetic radiation environment of its host star. Whether life could adapt to that environment is genuinely unknown. Some organisms on Earth, particularly in high altitude or high UV environments, have evolved extraordinarily effective UV repair mechanisms. Tardigrades, the microscopic animals famous for surviving extreme conditions, can withstand UV doses that would kill most organisms. Cyanobacteria in polar environments use UV-blocking pigments to protect their photosynthetic machinery. The history of life on Earth is a history of adaptation to conditions that initially seemed incompatible with survival. Perhaps life around red dwarfs has adapted to the stellar radiation environment over billions of years in ways we cannot predict from Earth-centric biology. Perhaps the answer is not whether organisms can adapt to UV, but whether the conditions ever allowed the emergence of life in the first place during the most active early phase of the star's history. These questions have no answers yet. But JWST is generating the atmospheric data that will eventually constrain the habitability of red dwarf planets in ways that replace speculation with evidence. The scale of what JWST is attempting is easy to understate. Light from K2-18b takes 120 years to reach us. During the time that light was traveling, every major event of the 20th century and the first 2 decades of the 21st occurred on Earth. 2 world wars, the development of nuclear weapons, the space race, the internet. All of that happened while the photons now arriving at JWST's detectors were crossing the space between K2-18b and this telescope. Those photons carry the chemical record of an atmosphere that existed 120 years ago. We are reading a message written before the Wright brothers flew at Kitty Hawk, before Einstein published the special theory of relativity, before the first radio transmission crossed the Atlantic. And the message contains molecules. Carbon dioxide, methane, possibly dimethyl sulfide. A chemical inventory of another world, written in light, transmitted across more than a century of travel, decoded by an instrument assembled by human hands and human ingenuity, and launched on a rocket that would have been science fiction when those photons began their journey. The gap between what we were capable of 120 years ago and what we are capable of now is the same gap between what we are capable of now and what we will be capable of when the light currently leaving K2-18b arrives at wherever our descendants are then. If those descendants exist, and if they have instruments, they will read a message we are currently writing into space with every photon that reflects off this planet's surface and begins the long journey outward. What story will that light tell about Earth's atmosphere in 120 years? The same oxygen and nitrogen and water vapor that tell the story of life? Or something different? Something changed by the chemistry we have been adding to our own atmosphere across the industrial era. The question of what K2-18b's light tells us about that world is inseparable, at some level, from the question of what Earth's light tells the universe about us. We are broadcasting our atmospheric chemistry across interstellar distances at the speed of light in every direction, continuously. Any instrument sensitive enough at the right distance could read our biosignature. We are already visible to anyone looking. The question is whether anyone is looking, and whether we will be looking back when the answer becomes clear. Thank you for staying with us until the very end of this journey through alien atmospheres, impossibly ancient molecules, and the question that has followed humanity since the first night someone looked up and realized the stars were not just lights. If this exploration changed how you think about what might be out there, if the idea that a telescope in space might be reading the chemical signature of life on another world made you stop for a moment and feel the size of what we are part of, subscribe and stay with us. The K2-18b data is still being analyzed. TRAPPIST-1E's atmosphere is still being measured. The Habitable Worlds Observatory is still being designed. Every answer JWST gives opens a question that did not exist before the answer arrived. That is not a limitation of science. That is science working exactly as it was built to work. Your curiosity is what the question demands. Keep asking it. The universe has been answering for 13.8 billion years, and it is not done.